So we have our second speaker today. It's Adriaan from Netherlands, and he's my student and Marcus Carlos' student. And we had the chance to actually, the aim of his thesis was our multifunctional unit, with the name we are not supposed to mention. And it's the building which has been actually installed in the new part of our office building. And Adriaan got the chance to survey the building, do some energy analysis and modeling of the building, and he came up with some good optimizations, but also his focus was on the energy sources. Like you said, we have lots of energy sources, different sources in Sweden we could use. There are others, so he also focused on the energy production method. And this is his bachelor thesis, and I'm proud to say that he did defend his thesis. He passed, so well done.
Yeah. Thank you, Petra. And thank you all for coming to my presentation, all 5 of you. Well, as you see, this is the building that you see probably every day. And I did an investigation about the newly built part of the office building in the green frame. And, well, I say let's start. In this presentation, I will first introduce the goal of the project, the scope of the frame in which I worked. With my analysis and methods that I used for the investigation of the building. After that I will show the results of my investigation and the conclusions and recommendations based on those results, both for the office building here in Venom and general recommendations for future projects. So the goal of this project is building optimization on energy and comfort level. And it was very important that we also focus on the comfort level, because you can make a very energy efficient building by not installing any lights or ventilation or whatever, and let people run on treadmills to generate energy. So you get a very good energy performance, but it doesn't say anything about the comfort level. So it was very important to have the best possible comfort level in the building, and then optimize the building on the energy level. And I did this through dynamic energy simulations. And with these simulations, I made a summary in Excel where all the results were put into a model, and it can compare with different energy production methods and different scenarios for the optimization of the building energy. And there was also a lot of information that was generated in this model. And that's also something I will show to you later in the presentation. And this was used to make all the conclusions for this project. And with these conclusions, these are the recommendations for the building. That's on the temperature set points in the building management system, on building adaptations for the office building, on the distribution adaptations for the ventilation, and recommendations on the energy production. And there will also be general recommendations for future projects based on all of these recommendations. So, reasons for optimizing the energy and indoor climate. Well, we spend a lot of time indoors, and it's important to have a good indoor climate to be healthy. It also helps with higher productivity and lower sickness. And below you can see the table that I've used. The indoor climate, for the indoor climate set points. The indoor climate is analyzed according to the PMV-BPD model, and there are more set points than just these set points, but these are the set points that you can regulate in this part of the building. So the class 1 comfort has a PPD of or lower than 6%, and that was our goal, to get to that percentage or below it, and then optimize the energy performance. And here's the building. It has a total floor area of almost 1,700 square meters, divided over 3 floors. It has been recently built, and it has been calculated with 75 occupants in total. Right now only the first and the second floor are being used, and the third floor will be used somewhere in the future. And in the simulations we also simulated the third floor as being used. And here in the middle you can see the office landscape, and on the sides are the conference rooms, which I will come back to later. Here's the multifunctional unit. As many of you may know, it's with the air handling module. the energy exchange module that gets the additional energy out of the extract air, the chiller and heat pump module that's connected to the energy exchange module, and the hydronic module with all the valves and pumps to get all the plumbing in one place. With the dynamic energy simulation software, I could only simulate the air handling module of the multifunctional units because the entire system is very complicated and the software did not allow to put that in the software very easily and would have taken a lot of time, so we couldn't get the entire multifunctional units in the software, but that's what we had the Excel model for, because I made some calculations in the Excel model with the energy optimization of the multifunctional unit. And the occupancy data is for both for the office landscapes and for the conference rooms. In the office landscapes there is a more general occupancy throughout the day between 30 and 50% for 25 persons per floor. And in the conference rooms there is a shorter occupancy but with higher peaks. And it's also different per conference rooms. There are different sizes of conference rooms with one person per 1.5 square meters. And this also takes into account extra people that could come from external companies. And so the calculation is done with EDA-ICE, which is dynamic energy simulation software. And the results of those simulations are put into the Excel model, and in the Excel model these numbers are used for the energy prices per kilowatt hour, and these are the efficiencies for heating and cooling that have been used, and those can also be easily adapted for future projects with different energy prices and different efficiencies for different locations. The adaptations that have been made is we start here with simulation 1 with the existing indoor climate and a combination of constant and dynamic demand-controlled ventilation. With the first three with these three simulations, there are no adaptations to the building, but only to the ventilation system. To the left, there's a 100% CAV system. In the middle, it is the current CAV DCV system, and to the right is a 100% demand-controlled ventilation system. And it's also important to know that with these simulations, all of these simulations, the indoor climate is already optimized. So the set points in the building management system have been set in such a way that we have a PPD of lower than 6%, but for the lowest energy consumption possible. And with the lower three simulations, again on left it's 100% CAV, on the middle is CAV DCV, and on the right is 100% DCV. But here the building is optimized with demand-controlled lighting in the conference rooms and with solar shading on the southern orientation of the building on the third floor. And these are the results from the simulations, quite a lot of numbers. It's important, this part is important, this is the total energy consumption per part of the energy consumption. So on the top we've got the total energy consumption for the multifunctional units, and that is calculated here, where in this column the total heating energy that is saved can be shown when there is a need for both heating and cooling. The multifunctional unit is set in such a way that it can use the heating energy from one side to cool, the hot water from one side to heat, the cooling, no, I'm messing it up. You know how it works. So the heating energy that's saved has been calculated with the Excel model. And the total lighting, this number changes of course with the adaptation of demand control lighting. The equipment, which is just the computers, the number doesn't change. And the total of building services, which include like the kitchen, outdoor lighting, elevators, those kind of things that could not be put in the Excel model as an additional internal load. So that's why we put it in the Excel model. and with a total energy consumption of simulation 1 of 115,000 kilowatt hours per year. So this was the first simulation, the one that was on top before the optimization of the indoor climate. And I've done that for all simulations. And this is a small explanation of the model that I'm about to show you in the next slide. Each simulation in combination with an energy production method has 3 numbers. The first is the efficiency, so that's the amount of kilowatt hours that can be consumed with this combination. So 1 kilowatt hour in the best possible scenario is more than 5 kilowatt hours out. And in the worst it's just 1 kilowatt hour. In the middle, this is the total cost in euro per year of operating costs. And here is the purchased energy per square meter for this building with all the different energy production methods. So then we get to this model, which is quite big. In the rows you can see the different energy production methods, and in the columns there are the different simulations that I've showed you before. So on top is the multifunctional units. And to the left is simulation 1 is where we start. This one has the highest operating cost in each simulation because it has not been optimized yet. And simulation 3 and 4 prove to be having the lowest operating cost. So I want to highlight those. And I also want to highlight the multifunctional units, energy production method A and energy production method B, which is an air handling unit with a chiller and district heating, which is a very common method in Sweden. But all these other energy production methods are common in other countries. For instance, with gas, it's pretty big in the Netherlands, where I'm from. So I want to highlight these two. Here you can see the multifunctional units and energy production method B with chiller and district heating. And here you can see the savings of each simulation. So in here you can see the differences in energy production between the multifunctional units and an air handling unit with chiller and district heating is 3,500 euros per year. And this is just a different energy production method. No set points have been changed, no adaptations. The only difference is a different energy production method. And with simulation 3 and 4, which are more optimized, you can see that the saving is actually a bit lower per year because less energy is used, so less energy is wasted. But they're compared, when you compare them, 13 to 17% can still be saved each year, just by having a different energy production method. And here is also a comparison with all the other simulations for production method A, the multifunctional unit, and B, the air handling unit with chiller and district heating. So here you see the different simulations. And simulation 3 with demand controlled lighting has been added. Simulation 3 is, the original simulation 3 is the current building with 100% demand controlled ventilation, but we also wanted to investigate the building without the adaptation of the solar shading, so only with demand controlled lighting, which proved to be very energy efficient. So there's a very small difference between these energy consumptions. And so this is for the energy production. So here you can see the difference of the multifunctional units and energy production method B. And this red area is just all the energy you save if you would use the energy production method A, the multifunctional unit, which is quite a considerable part. If you look at simulation 1, it's 115,000. And with B it's 155,000, so it's quite a considerable amount of energy that can be saved. And here is the same table but with the energy prices. You see the same tendency here with the red area. It's a bit smaller, and that's because district heating per kilowatt hour is a bit cheaper than a kilowatt hour in electricity here in Finland, Sweden. Um, so, in conclusion, the best simulation is the building with demand-controlled ventilation and demand-controlled lighting. The best indoor climate is achieved with a PPD of lower than 6%. Optimizing the temperature set points and minimizing the nighttime ventilation, which is the first step to do with optimizing the indoor climate, saves almost 9,000 kilowatt hours per year, which is equal to about 1,100 euros per year in operating cost, and it's 7.5% of savings in operating costs each year, just by optimizing the temperature set points and guaranteeing the best indoor climate for the lowest energy consumption. Additionally, including 100% demand-controlled ventilation saves almost 6,000 kilowatt hours per year. When I was investigating the building management system, I saw that there was a lot of constant ventilation, even though the demand-controlled ventilation equipment has been installed. For some reason, the set points had not been set in such a way that demand-controlled ventilation could be achieved. But by doing that now, you can save about 750 euros per year in operating cost. And applying the demand-controlled lighting saves almost 4,000 kilowatt hours per year, and that's just in the conference rooms. So that's just installing a sensor, and then you've got that. All adaptations combined save more than 18,000 kilowatt hours per year, with and saving annual saving of almost 2,400 euros per year. So that's almost a monthly salary for me. It would mean that almost 16% of the operating costs can be saved each year just by optimizing the temperature set points, optimizing the airflow set points to guarantee demand-controlled ventilation, and minimizing nighttime ventilation, and installing demand-controlled lighting. The best energy production method proved to be the multifunctional unit, with it had the highest energy production efficiency between 5.09 and 4.29, depending on simulation, and the lowest operating cost per year in each simulation between 15,000 and 12,360 euros per year. Compared to energy production method B, the airline units with chiller and district heating, 19 to 26% can be saved each year on produced energy, and 13 to 18% can be saved each year on operating costs just by installing the multifunctional unit in this building. Compared to the second best energy production method, the air handling unit with a chiller and a heat pump, it saves 1 to 2.4% each year. And now this may not seem like a very big percentage, but the multifunctional unit only uses a chiller or a heat pump in the module. And this is two systems. This is a chiller and a heat pump compared to just one system in the multifunctional unit. So you can save on the installation cost of one less production method with the additional wiring and plumbing and everything. And also part of the multifunctional unit is that everything is combined into one machine, so if something is wrong, there's one place to go, and that's the multifunctional unit. So you can save on the investment costs if the multifunctional unit proves to be the cheaper in investment, but you also save on the operating cost each year, while still guaranteeing the best possible indoor climate in this building. And the multifunctional unit proves to be better than energy production method C, because there's a heating and cooling need in the building at the same time. And if this would not be the case, then the savings could be a lot less, or even zero, when compared to energy production method C. So the recommendations for the Swegon office building are as follows. In the bottom you can see the current set points in the building management system for temperatures, both for when the room is occupied and unoccupied. The red frames are the ones that are changed with 1 or 2 degrees Celsius. So it's just 1 or 2 degrees Celsius. It's not that much, but it makes quite a difference. So all the heating and cooling set points for when the room is occupied are the same, and before they were different. So the cooling set point is 23 degrees Celsius, and the heating set point is 21 degrees Celsius for when the room is occupied. And when it's unoccupied, the cooling goes to 25 degrees Celsius, and heating goes to 19 degrees Celsius. So there's a difference of 2 degrees Celsius in each case. It's interesting that the model from Vanger, the PNV-PPD model, suggests 21 degrees to 25.5 degrees within the to use as set points for the indoor temperature, but it proved to be that 21 to 23 degrees Celsius was the best for the training office. Applying demand control lighting in the conference rooms is a recommendation. The minimum required ventilation seems high. This applies to the nighttime ventilation with a minimum ventilation of 0.35 liters per second per square meter. This is not the current case. There's a lot of constant ventilation, so there's a lot of ventilation at night as well. Right now the ventilation is around 600 liters per second. And it could go down to 250 liters per second for the first floor and 230 for the second floor, and these are described in more detail in the thesis. But this could save a lot of energy. And table 9.5, which is this table, can be used for when the third floor is being used and all the comfort modules will be installed. Then these numbers can be used spread out over the entire floor to guarantee the best indoor climate for the best energy consumption. And general recommendations for the future projects with the multifunctional units are that if there's a proper research about the design of the building and about how much that could save with demand controlled ventilation, the air handling unit could be downsized at least one size, which can save on the investment. It is very important to make sure that the building management system guarantees 100% demand controlled ventilation when this equipment is also installed. Like I said before, this for some reason was not done before. Very likely reason is that when the building was first being used, there was a lot of ventilation to get all the emissions from all the new materials out of the building, which is quite understandable, but well, someone puts in a number and then forgets to put the number to something that guarantees demand controlled ventilation, which is a shame because this way a lot of energy is used that doesn't have to be used. So it's good to make a checkup with the set points in the building management system to guarantee demand controlled ventilation. Only a chiller or a heat pump is needed when the multifunctional unit is installed, instead of two different systems, for one for heating and one for cooling. And this can also be, like I showed you before, saving both for the investment and for the operating cost, while still guaranteeing the best indoor climate. And large fluctuations in occupancy make it more feasible to install demand controlled lighting. This is also something just for user comfort, so you don't have to switch anything on or off. It just goes on when you enter the room and it goes off a few minutes after you leave. And this can save a lot of energy power from the lighting. It's also very good to research the possible temperature set points for the desired boundaries, and with boundaries I mean what kind of indoor climate you want to have. If we would, for instance, would have gone for class 2, which would have a PPD of lower than 10%, the temperature set points could have been more far apart, which would save more energy, but you would not have the best possible indoor climate. So within the frame that you set for the indoor climate, it's good to investigate these temperature set points to save more energy while still guaranteeing the desired climate, hopefully the best possible indoor climate. And this recommendation is for the Excel model, and I'm actually working on this right now, where simple numbers, simple figures can be used to put into the Excel model. This is for heating, cooling, the building services and equipment, and the heating and cooling part is the most difficult part to properly investigate. But this way the model can be used more easily also for salespersons, so that a comparison can be made between different energy production methods and different scenarios, for instance, where there are different energy consumptions for different situations or for the same situation. And that way it can easily show which energy production method is the best in which case, and it can also show where if the multifunctional unit for some reason does not seem to be the best possible choice, it could also be a reason to see, hey, well, maybe there's something we need to innovate on. The best indoor climate is guaranteed, and there is a possible energy saving of 16% on energy use, with 18,000 kilowatt hours saved per year, saving almost 2,400 euros per year on operating costs each year. Thank you for your time.
Thank you.